Hi everyone, welcome to watch my talk. I'm going to present my KAI 2020 work, MaraVis, Representation and Coordinated Intervention of Medical Encounters in Urban Medicine. I'm Chen, a research scientist from Weibach, China. This is a joint work with Tencent and the Hong Kong University of Science and Technology. As we know, marathon is long-distance running event that covers an official distance of 26.22 miles. Given the scale of participants, preparing a marathon event requires significant efforts, including the design and implementation of racing courses, communication systems, and resource management. Lots of work has been done regarding the situational awareness in urban marathon. For example, during a marathon, participants may encounter medical incidents such as falling down, arrhythmia, and heat stroke, as well as other unforeseen incidents like lagging too far behind or running off the racing course. If danger happened, runners could receive help from the aid stations distributed around the racing course. Some work has been proposed, for example, SAFE incorporates critical data into a dashboard, which provides a pre-event and on-site analytics and monitors dynamic location of race participants, as well as managers health and safety resources. Tencent panels provides dashboard visualization for city marathon event, which shows geographic distribution of participants and outline list. Meanwhile, it has very cool visual efforts. In this work, we propose MaraVis, a real-time visualization system that supports better representation and coordinated intervention of medical encounters in the massive urban marathon data stream. This figure is an overview of MaraVis. Its mainly consists of 4 views: marathon overview, anomaly detection view, camera shoot view, and HRV inspection view. First, I just present a short video to quickly go through MaraVis. The collaboration and the deployment of Tencent panels provides us a dataset that records a local 2-hour, 20 km half marathon event. We propose the data in 3 aspects. First, the urban environment is simulated in a 2.5D map, which displays major roads and buildings. Also, service and aid stations. It contains event participants, including runners, volunteers, and event organizers. The trajectories are processed, which includes time step, heart rate, peak-to-peak interval derived from PPG data, speed, pace, cadence, distance, longitude, latitude, and ID. MaraVis mainly deals with 2 things. The first is anomaly detection. It contains of 4 parts. First, real-time anomaly detection. We check runners' attributes in every 5 seconds and evaluate whether any value are outside the normal range. Second, stage anomaly detection. We determine potential anomalies based on the accumulated data within a predefined time window and detect outliers by LOF algorithm. Third, we update the potential anomaly list by displaying results from step 1 and 2 and mark anonymous runners with different occurrence number. Step 2 is HRV inspection of anonymous. It facilitates medical groups to leverage more information to analyze the outlier runners, including time domain, frequency domain, and geometry metrics. Furthermore, we use an LSTM model to detect atrial fibrillation AF bits in HR signal to confirm the real anomalous runners. Here is a short video description of anomaly detection process. Having determined a set of events, our next task is to compute an optimal sequence for the entire flight by training each event and show each of them to maximize the total quality. Particularly, the camera control employs different camera shot designs and generate an optimal route to catch the detected anomalous events to enable a smooth online and offline intervention. We propose two algorithms, namely algorithm 1 and 2, to compare with the baseline methods. Particularly, the baseline shows events one after another. Algorithm 1 is a 3D routing problem by leveraging a 3D Euclidean distance, and algorithm 2 minimize the cumulative gap between spatial and temporal distance. Here is a short video description of the three camera training algorithms. Along the camera route, we use different types of camera shoots. The reason is that different shoots can facilitate swift response through view shift. Because the screen space is very limited, it's important to display the most important scene. Also, different camera shoots can visualize different event information such as event object, occurrence time, and location. Particularly, we use normal shot to check the objects from the side. Panorama shot is slowly move the camera over a landscape with a wide open space. A following shot to follow the subject being filmed around. A dolly shot to move the camera towards or away from a subject while filming, and a split screen to divide the screen and show several images simultaneously. Here is a short video description of the camera shot design. First, the camera used a panorama shot. Something happened, and then the camera changed to a dolly shot, followed by a normal shot, and finally turned to a panorama shot. To evaluate our system, we invited 18 participants, including 9 females and 9 males with around the age of 28 from the local marathon organization. We compare MaraVis with a baseline system panels and a primitive system MaraVis. We counterbalance the three systems and ask the participants to observe and check the potential anomalies and evaluate camera mode training algorithms. Particularly, we asked the participants several questions about informativeness, decision-making, visual design, system usability, and view training. Regarding the informativeness, we find that both versions receive significantly higher scores in all metrics of informativeness than the baseline. No significance has been found between full and preliminary version in accessibility. Information provided by full and primitive version is significantly richer than the baseline. And there is a difference between the two versions regarding the richness. Information offered by both versions is sufficient in determining an anomaly compared with the baseline, and no significant difference between full and the primitive version in sufficiency. Regarding the decision making, we also find several conclusions as shown in this screen, and I will not repeat it one by one. And regarding this usability, we also find several conclusions, and the main conclusion is that users are more willing to recommend the two versions than the baseline, and no differences exist between the two versions. Regarding the visual designs, we find that anomaly detection design in the first version is not more intuitive or comprehensible than the final version. And regarding the conflicts of the camera move training, we find that fewer conflicts of algorithm 1 and 2 compared with the baseline, and no significant difference between algorithm 1 and 2. Regarding the smooth and coherent of camera move training, we find that significant difference regarding smooth and coherence exists between the two algorithms, while the baseline is in the middle. and there is also a significant difference between algorithm 1 and 2. This is the same with whether the methods give the audience a sense of following a reasonable route. MaraVis has a good generalizability in terms of visualization, data, and algorithm. Particularly, the visualization is easy to understand without too much training. MaraVis covers most of the common data coming in and out a marathon control center, and it has all well-defined APIs for each module. With this setup, we can easily replace the back-end algorithm when necessary. Regarding the scalability, when dealing with a large data stream, we can use data sampling. When discussing about the learnability, we find that the preliminary version of system may be a good start to allow the experts to familiarize themselves, and we can also take this chance to test the initial designs. Our system has several limitations. First, we do not consider individual difference in anomaly detection. Second, no ground truth to verify the rate, the error rate, the accuracy of the anomaly detection reported by our system. Third, currently we focus on camera training and shot designs and have not replied and tested in real videos, and they are based on ideal situations. Now come to conclusion part, and in this work, we propose a real-time marathon visualization system that supports better representations and intervention of medical encounters. We identify potential anomalies to quickly follow up with critical medical incidents, and we calculate an optimal camera route to catch events in time and make a smooth view transition by using different shot designs. In the future, we will deploy our system in a real-time marathon and field study and extend the camera shot design to a formal and comprehensive design study. So, that's all. Thank you for your time and wish everyone safe and health.